Okay. Good morning, students. Welcome to the live lectures of real analysis. So first we will see in today's lecture. First we will see what is meant by Cauchy sequence. Cauchy sequence. We know definition of sequence. It is a function from set of natural numbers to R. Then it is called as a sequence in R or sequence of real numbers. And we have seen definition of convergent sequence also. When we say that xn is convergent sequence, if for every epsilon greater than 0 there exists natural number n0 such that mod of xn minus x is less than epsilon for all n greater than equal to n0. Now we have to see when xn is said to be a Cauchy sequence. So we'll define xn, the sequence xn is said to be Cauchy if for given epsilon greater than 0 there exists natural number n0 such that mod of xn minus xm is less than epsilon for all n m greater than equal to n0. Can you see this definition? Yes. So what is the difference between convergent sequence and Cauchy sequence?
Every Cauchy sequence is convergent.
No, I am asking what is difference means.
Ma'am, there is xn minus x and here xn minus x.
X. So what is in Cauchy sequence? What is there? We need not have like here distance between any two elements will be small. Xn and xm are two elements of that sequence. If distance between any two elements after some stage, let's draw the diagram. Means we should find after some natural number or after some stage, distance between any two elements will be very small. It will be. Is that okay? And in convergent sequence, distance between xn and that x will be small. This xn and xm are nothing but 2 points of that sequence. Is that okay?
Yes, ma'am.
And Cauchy is name of scientist, so mathematician. So make sure whenever you use Cauchy name, you use C as capital letter. Okay. We'll take examples and all that. For example, 1 by n is also Cauchy sequence. For example, xn is equal to 1 by n is a Cauchy sequence. Okay, now we have to prove some theorems based on this theorem. Every Cauchy sequence is bounded. Every Cauchy sequence is bounded of real numbers. Every Cauchy sequence is bounded. We have to prove every Cauchy sequence is bounded. How we can prove? Proof. Let xn be a Cauchy sequence. And we have to prove it is bounded. So, since it is Cauchy, for every epsilon we will have a natural number. We will have a natural number satisfying this property. Okay. Because it is Cauchy, there exists a natural number such that this one. So, for every epsilon means in particular for epsilon is equal to 1 also we can have a natural number. Right?
Yes, ma'am.
So, Cauchy sequence for epsilon, then for epsilon is equal to 1, there exists natural number n0 belongs to n such that mod of xn minus xm is less than epsilon for all n m greater than equal to instead of n mod I will use p here, p or k, whatever, k also we can use, n m greater than equal to k. Is that okay? This is by definition of Cauchy sequence. Now I want to show it is bounded. When I can say this xn is bounded, if I can find a real number m such that mod of xn is less than equal to m for all n, right?
Okay.
Yes. So consider mod of xn. Mod of xn, how can I write? Xn, I want to xn minus xm plus xm I can write.
Yes, ma'am.
Then xn minus xm plus mod of xm. Yeah, instead of xm, because here k we have used, so I will write here k. Instead of m, I will use k. Add and subtract xk. Then we can use, or p also, whatever. Okay. Now xn minus xk, what can I say? It is less than epsilon because n,
Yes, ma'am.
when m is k greater than equal to k, so this is less than 1, right? Mod of xn for epsilon is equal to 1, we are having this now. Is that okay?
Yes, ma'am.
So plus
Yes,
mod
ma'am.
of xk, but for this is for mod of xn is strictly less than 1 plus mod of xk. But what is mod xk? We have already proved such theorem. When I can write this for all what is this? Where I can use this?
N comma m.
For all n greater than equal to k, for all n greater than equal to k, I can use, means mod of xn minus xk will be less than 1 plus mod of xk.
Yes, ma'am.
Yes. Now what can I say?
Since 1 plus xk, m, we
Yes.
suppose m
So
maximum of
I want to show this is less than equal to some constant for all n, not only for n greater than equal to k. For all n greater than equal to k, I am having this upper bound. for all n greater than equal to k, I am having this upper bound. What about previous one? Like suppose x1, x2, and nothing but xk, xn, xn plus 1, and so on. Okay. So after this stage, we are having this. For all n greater than equal to k, mod of xn is less than 1 plus mod of xk. So we don't know about this. So what can I do? Take
maximum of.
Take m is equal to maximum of that elements, whatever may be, mod of x1, mod of x2, and up to which? Mod of xk minus 1. And for n greater than equal to k, I am having this one, 1 plus mod of xk. Right? So this m will work for all n. This implies, or then can I say mod of xn is less than equal to m for all n? Can I say? Is it okay?
Yes, ma'am.
Therefore, sequence xn is bounded. Therefore, xn is bounded. Okay, so every Cauchy sequence is bounded. Like in previous we have shown that every convergent sequence is bounded. Now we have to prove next theorem. If xn is Cauchy and xnk a subsequence and subsequence xnk converges to x, then xn also converges to x. What this theorem says that, what is given here? Xn is given to be Cauchy and we have given a subsequence which converges to x. Then we have to prove xn converges to, means that original sequence converges to x. So earlier we have proved if every subsequence converges to x, then that sequence also converges to x. Or if sequence converges, original sequence converges to x, then every subsequence converges to x. Right? If sequence is convergent, then every subsequence will be also convergent and has the same limit. Right?
Yes, ma'am.
Yes.
Yes, ma'am.
But now here, what is difference here? Not every subsequence, but if it is Cauchy and if we are having a subsequence which converges to some element, then that original sequence also converges to x, that we want to prove. So proof let xn be a Cauchy sequence and assume xnk there exists a subsequence xnk converges to x. And what we want to prove? Xn converges to x. So start with arbitrary epsilon. Okay. So let epsilon greater than 0. So for this epsilon, since xn is Cauchy, what will happen?
xn minus.
Then there there exist natural number. There exist a natural p1. Say p1 belongs to set of natural numbers such that mod of xn minus xm less than epsilon for all n m greater than equal to p1. Is that okay? Because what is the reason? Because xn is Cauchy, right? Yes. And also what is given? Xn k converges to x. Again for this same epsilon, also since xn k converges to x, there exists another natural number, say p2 belongs to n, such that mod of xn k minus x is less than, instead of epsilon I can write epsilon by 2 also, na? Right?
Yes, ma'am.
Yes, ma'am.
Epsilon by 2 for all k greater than equal to p2. Nk is greater than equal to k and k greater than equal to p2, right? For all nk greater than equal to p2 or nk is greater than equal to k greater than equal to p2, I can say, right? So I am having, this is 1 and this is 2. Now consider mod of xn minus x. I want to show this is less than epsilon for all n greater than equal to, okay? So or instead let p is equal to maximum of p1 comma p2, then consider, okay? Let p is equal to maximum of p1 comma p2. Consider then mod of xn minus x. How can I write? Mod of xn minus xm plus xm minus x. Add and subtract xm, right? If I use triangle inequality, I can write this as mod of xn minus xm plus mod of xn minus x, right? Now our p is equal to maximum of p1 comma p2. So what can I say?
Yes, supremum.
No. So okay, let p greater than equal to maximum of p1 p2 and we will say n, because n we want, na? N greater than equal to p, say. Then instead of m, because we are having here in terms of subsequence, I will write here add and subtract x and p term, okay? In terms of subsequence, I will take. NP. Now you can tell. What can I write? xn minus xn p. N greater than equal to p. And p is nothing but my maximum of p1 comma p2. So what can I say about xn minus xn p? It is less than epsilon by 2. Huh?
Yes, ma'am.
Yes. And this is xn p minus x is also less than epsilon by 2. Right? So it is also less than epsilon by 2. Using, we can write here using 1 and 2. We can write. And which is less than epsilon. So there exists natural number p such that mod of xn minus x is less than epsilon for all n greater than equal to p. Is that okay?
Yes, ma'am.
So this implies
Yes, ma'am.
xn is xn converges to x. I can write convergent sequence or converges to x. Xn converges to x. So if it is Cauchy and we are having at least one subsequence which converges to x, then we can say. But if it is not Cauchy, and if we are having some subsequence converges to some element, we cannot say it is a convergent sequence. Okay. For example, you consider this sequence minus 1 raised to n. Xn is equal to minus 1 raised to n. Can you give a subsequence which converges? Xn k is equal to 1. You can take constant sequence. It converges to 1, right? But this xn, since it is not Cauchy, this xn does not converges to 1. Okay, if this original sequence is Cauchy, then we can say it will converge. Is that okay? So Cauchiness is necessary condition. Is that okay? Okay. So now take next theorem. If xn converges, then xn must be, then it is Cauchy. You can easily prove this. Can you prove this? So let xn be a convergent sequence converging to xn. That is xn converges to xc. And what we want to show? And my claim is we want to prove xn is Cauchy. So what we will do? Let epsilon greater than 0.
0.
Yes. So whenever we want to show it is Cauchy or convergent, we have to start with arbitrary epsilon. So for this epsilon, we should find a natural number p. So which satisfies condition mod of xn minus xm is less than epsilon. Okay. So how can I start? Then
N greater than
there exists natural number p such that
N
mod of xn minus x is less
minus
than
N.
epsilon for all n greater than equal to p.
P.
So okay, greater than equal to p. Now for this epsilon I want to prove, then the same p will work for this. Now consider mod of xn minus xm. Now add and subtract what?
X.
X plus minus, which is less than or equal to mod of x minus x plus mod of x minus xn. So consider nm greater than equal to p here. Then let nm greater than equal to p. Now consider xn minus xm. Okay. Now n and m greater than equal to p. What can I say? It is less than epsilon.
Epsilon by 2.
Yes. So instead of epsilon, I will write here epsilon by 2 and epsilon by 2. To make it epsilon, I am taking epsilon by 2, epsilon by 2. Is that okay?
Yes, ma'am.
Using 1. So which is nothing but epsilon. So mod of xn minus xm is less than epsilon for all n m greater than equal to p. Therefore, what this implies? This implies xn is a Cauchy sequence. Is that okay?
Yes, ma'am.
Yes, ma'am.
Okay. Next theorem is completeness of R. Set of real numbers. Completeness of set of real numbers. What is completeness? Completeness property. Every Cauchy sequence in R converges in R. Every Cauchy sequence in R converges in R. Means every Cauchy sequence of real numbers converges to again a real number that we want to prove. So how can I start? Let xn arbitrary start with arbitrary sequence. Okay. Start with arbitrary sequence. So let xn be a Cauchy sequence in R. And what we want to prove? So let xn be a Cauchy sequence in R. And we have already proved every Cauchy sequence is bounded. This implies
Yes, ma'am.
xn is bounded by previous theorem. Okay, xn is bounded. Now every bounded sequence of real numbers has a convergent subsequence. We already proved.
Yes, ma'am.
This implies there exists a subsequence xnk convergent subsequence, okay, or xnk converges to x in R. This is by what? Then by Bolzano-Weierstrass theorem. Weierstrass theorem. There exists a subsequence xnk converges to x in R. Now what can I say? So my xn is Cauchy and I am having a subsequence which converges to x in R.
So if subsequence converges, then the
Just now we have proved. Here we have proved this one. Xn is Cauchy. This theorem we have proved. Xn is Cauchy and there exists a subsequence. Then that Xn also converges to X. Right? So from here to here I can copy and paste the proof. Right?
Yes.
8 minutes. 1 second.
When you started.
We have already proved now this theorem. If Xn is Cauchy,
Yes, let Xn.
Ithun, let epsilon greater than 0. Ithun. Is that okay?
Yes, ma'am.
Xn converges to X. So just we have to, since it is Cauchy, we have to use, then it implies it is bounded. So by Bolzano-Weierstrass theorem, there exists a subsequence which converges to X in R. Now you can directly also you can say in one line, but if it is for 8 marks or 6 marks, then you have to write the proof. Okay. So this implies every Cauchy sequence of real numbers converges in R. That is R is complete. Set of real numbers is complete. Okay. Is that okay? These are all theorems related to Cauchy sequence. Is that okay? Now we will just write
Yes,
a
yes,
statement of the theorem. Again, one theorem we can construct. Theorem. The sequence Xn in R is convergent if and only if it is Cauchy. Means every convergent sequence is Cauchy and every Cauchy sequence is convergent in R. Is that okay? Every Cauchy sequence of real numbers is convergent and every convergent sequence of real numbers is Cauchy. But if it is not real numbers, it is not true. That we will see in metric space. Okay, when we start metric space and completeness, then we will prove this. This theorem is only for set of real numbers, not for any metric space. Okay. So this theorem this proof you can you prove this? Suppose Xn is convergent sequence, prove it is Cauchy. Already we have proved the theorem, right? Let Xn converges to X, then we have proved it is Cauchy. And conversely assume it is Cauchy and then you prove it is convergent. Is that okay?
Yes, ma'am.
So proof you can take as exercise. Just we have to write the proof of above two theorems. Is that okay? So this completes Cauchy sequence. Next section.